So yeah, I was asked to talk about Sirepo, and you know, it's a very Sirepo is a framework for cloud computing to do beam dynamic and also optical simulation. And one of the advantage of this framework is that it allows you to set up problem in with a GUI and the web interface. So there are many flavors of the Sirepo, and they are shown on the right side. And basically, Sirepo is really a high-level layer, and it connects to many open source software that have been developed by the community. So the one I choose today is SRW, which stands for the Synchrotron Radiation Workshop. And the reason was that it was a good connection with what Georg was talked about. But there are, as I said, many flavors. Some are related to beam dynamic, like Opal, which is a space charge program similar to GPT or Astra. Radia to design magnets, Elegant, that many of you know, which is a single particle tracking codes. So I'm going to attempt to do everything live. Of course, the problem with that is there might be some issue, especially if many of us try to run on the same problem simultaneously, because the simulation are performed on the cluster at Radiasoft, which is the company which developed Sirepo. So let me. So I think if you want to have this as a hands-on training, you can launch. You have to request a link so that you open your own workspace, and then you will click on the link I have in the other part of the talk to download a copy of the project I set up. And I set up 3 projects. One is a very simple project to illustrate the use of SRW or Sirepo to understand, you know, diffraction through a single rectangular slit from the near field, so the shadow, up to the Fraunhofer diffraction pattern. Another example is again in the you know, imaging and Fourier optics is the use of 2 lens to filter an incoming sources and to choose which part of the source you want to highlight using Fourier-based frequency filtering. And the last one is aligned with what Georg presented, is to show some property associated with undulator radiation. And then you can later, you know, combine undulator radiation with, you know, the lenses and do all kind of things. And by the way, it turned out SRW, Sirepo SRW is what we use to do most of the simulation, I think both at Cornell and at NIU Fermilab for the optical stochastic cooling experiment, where we model the transport of the undulator radiation produced by the first undulator, and then use the imaged radiation in the second undulator to compute the kick and the impact on the electron beam or on the electrons. Okay, so let me say a few words about Sirepo SRW first. So this was a code developed, I think, in '98, actually, by Oleg Subar at ESRF, which is a synchrotron radiation source facility in Grenoble, France. And initially, it was developed to model and design X-ray beam lines. It's over the year, it evolved, and it, I think, last maybe 5 years, it was ported to Python, and so it has a high-level interface based on Python. And under the hood, all the heavy calculation are done in C++. So it has 2 modules. One is a wave optics capability, so it means that it uses a simple scalar diffraction model, so based on the Kirchhoff integral, which is this convolution integral, and it doesn't really do a convolution integral. It does this numerically using FFT algorithm. And so you can set up a source, and then you can study how this source evolves on a 2-dimensional transverse grid. And so because this is based on this Kirchhoff integral approach, it's not a time-dependent, you cannot have a time-dependent source easily. What you have is a monochromatic wave, which is assumed to be CW, so infinitely long in time. And then you study its transverse evolution over different coordinate along a beamline you are interested in. I should point out that for instance, for optical stochastic cooling, where we have a finite pulse, what we do, we basically use Fourier transform or the Fourier theorem. We transport many monochromatic waves with a proper amplitude to synthesize a given optical pulse. And then you combine them and you can have the time domain distribution of your pulse. So this can be used actually to model laser pulse transport for, we did this from laser to the photocathode to understand, how you can shape the beam. Or this can be used to directly transport the radiation from different systems. So the second module is a radiation source module, and what it does, it solves the linear Vickers potential at a given in the Fourier space, so at a given wavelength or frequency, and then you can then use the wave optics capability to just transport this optical wave produced from an electron beam down your beam line. And this was originally the way it was used. People would, have their undulator or bending magnets, use SRW to produce the radiation, X-ray radiation typically, and then they would have a bunch of optics, grating, and all these things to study how this radiation evolve and how to optimize the transfer beam line until their sample to set up their experiment. So this is really SRW is what is under the hood, and Sirepo SRW is the GUI, which is a high-level interface, web-based, and it also have cloud computing. So it means that what we are going to do now is, on the web, and you use a cluster which is located in Colorado at Radiasoft. So let's start with the first example I wanted to show. This is the web page, and I think if you clicked on the right link, you should have access to the example. And now, if you actually, I should probably do it from here. If you click on this, you will end up in on an example, which is an example I set it up. But the way I did that is that I did the exercise of setting up an example that I hope will work. But then I remove all the module and I just put the source, and then we will build together the module to repeat what I did. So what I wanted to illustrate with this example is a simple propagation of a Gaussian beam like a laser, and like your Hini laser, it's a CW beam, so continuous, and just has a certain Gaussian shape transversely. So most of the tools in Siripo, or most of the flavor of Siripo, they have several tabs. One is about the source, and one is about the beam line. So in the case of SRW, the source is going to be how you specify your initial beam. In the case of Opal, for instance, the source is going to be what kind of particle distribution you want to use. If you want to load your own distribution, which you can do by uploading your own file of microparticle, or if you want to use an internally generated particle distribution. So in this case, I prepare, so if I click on Gaussian beam, I prepare a Gaussian beam which has a 1 millimeter waist at 0, so at the starting point. It has a horizontal polarization, and then it has a 1 eV photon energy. So there's nothing very exciting here. And when you set up your beam, what will appear on the right is the intensity of the radiation, the intensity distribution associated with this beam at a given location. And I selected 0.5 meter, and yeah, that's what I selected just for illustrative purpose. By the way, I noticed as I was playing with this, I noticed some little annoying bug, which I think are due to the use of Sirepo for both wave optics and radiation simulation. For instance, here it's a single electron intensity, but this has nothing to do with single electron intensity. This is no radiation. This is a coherent Gaussian beam that was started. So you can ignore this subtitle here. So then we can go to the beam line, and there we can set up a problem. And what I said I wanted to do was to put an aperture. Actually, what the problem I want to study or to demonstrate is to take this Gaussian beam, put an aperture, and then look at the pattern in the transverse pattern as a function of different z. And what you expect from undergrad textbook is that depending on the Fresnel number, you are going to first have a shadow of the aperture. As you decrease the Fresnel number, the Fresnel number, you are going to have a Fresnel pattern. And eventually, as the Fresnel number become very small, this pattern is going to go to converge toward this Fraunhofer diffraction pattern. And in between, you would have something which is a hybrid thing between the two type of patterns. So I'm going to set up this problem, so a very simple problem to start with. The first thing I'm going to put is an aperture, and the way you do this, it's very simple. You just drag the aperture in the wave in the beam line, and then you just select what kind of aperture you want to use. And I am cheating here because I'm looking to what aperture I used before to make sure I get something which makes sense. So I'm going to use an aperture of 0.5 millimeter, and maybe in vertical I'm going to use it as 1 millimeter, and I'm going to make it rectangular, so you can have circular, rectangular. So then you can close this, and since you want to view the beam downstream, or the distribution downstream, we are going to have to add a watch point. And so I'm going to add a watch point, and the first thing I want to show you is that if you make this watch point very, very close to the aperture, you should see just the shadow of the aperture. And once we have this, we can save change, and then it's going to run. So it's going to run again to show the intensity distribution, which now I put at 6. I should have said this at 0.6 meter from the source, and then the intensity watch point, which is going to be just behind the aperture. So now you see. The beam passed through the aperture. This was a Gaussian beam, and it's kind of clipped almost uniform because the RMS size of my Gaussian is not very large. It has this parabolic shape. So here, nothing exciting, right? You are just looking at the shadow. But now, if I put one more aperture, and now I go slightly further away from this, so let's say 0.6. Let's say 6.1, I think, was giving me something. And then run again. Then you will see. So now it's taking a little bit more time. And you should see something that looks like the Fresnel pattern that was shown here. And you see this is kind of what you are seeing. If you look at it, you can see the same pattern as what is here for z equal 100 over k. I should say that right now I did not tell anything about how many grid points you choose, and there is some kind of recipe to do this, and I let the software do this by itself, and this is just in for sake of running time. I could have a much finer grid pattern, but then it will take way more to run, especially on the cloud. So now I'm going to remove this guy because it's not interesting, and I'm going to add one more watch point, but far away, to compare the Fresnel and the Fraunhofer pattern. So I think if I do 1 meter here, or maybe 1 point. And run this, I should see both the Fresnel and the far fields of Fraunhofer pattern. So let's see if it works. So now you see, well, maybe you cannot see very well, but you can see a little bit of side lobe. And the way to convince yourself of this is, let me do this and move so to see the projection. So if you look, well, it's very hard to see, but you can see the side lobe starting to appear here. So that's the Fraunhofer pattern. So again, as I said, this is a very simple example to start. And as I said, though it's a simple example, if you want to do a nice simulation, you need to run this with a finer grid. And the last thing I want to show you about this is that what you can do then is you can, you can then, maybe you have actually the real SRW installed on your computer, on your cluster. And if you do this, then you can download the Python source. And let me just, I forgot if it's the same, but let me just show you. This was one. So, and that would be, what you would have had to type to actually prepare a script for SRW. So this, of course, it's a bit more general here. Something can be deleted, but the point is what you did with these three icons here and defining the source avoid you, let's say, typing 1/3 of the script roughly once you remove whatever is not needed. So it's very convenient to set up a simple problem, learn about the code, and then get the script generated, and then do the real calculation on your computer or cluster. And this is the approach we actually took for instance, the optical stochastic cooling. Okay, so the second example I want to show is filtering. So now it's kind of imaging and filtering. So let me go back. So I think I can close this one. Let's see, let me close this one. Let me just click. So if I click on this guy, oh, it doesn't want to work. Let me just put it. Okay, so now what I did here, I just did the little trick to make a source which is uniform. So I just use exactly what I had shown you before. So I had a watch point just to look at what's coming in. I put an aperture, and then I put a watch point just after the aperture to look at to make a uniform path. And what I want to do now is build a system like this. So I have my object, which is my uniform source. I'm going to put a lens, which is at a length, which is the focal length. And then I'm going to look at the downstream of this lens at an equal length, again, the focal length. And this system is what allows you in optics to do an analogic Fourier transform. Basically, this focal plane is a Fourier transform in the spatial domain. And so what you have is kx and ky. So if you do some filtering here, putting a mask, or in our case, we are going to put an obstacle to change instead of using aperture, you can select which frequency you want to transmit. And then if you build the symmetric of this, let's say for simplicity, the same lens with the same distances, what you will do is you will provide an image of this object, but with some of the frequencies suppressed. And this simple example of this black E becoming an E, what happened is, what was done is that a mask was put at the center so that the low frequency, which is where the object appear more constant in intensity, are suppressed. And at the end, you highlight the edges of the pattern. So in this case, the edges of the E. So let's try to do this example or to set up a similar case. So let me just look at my cheat sheet of what I did to use the same parameter, so I have something working. So I'm going to, I have used a watch point, and the first thing I'm going to do is put this first lens. So let's put a lens. So again, you drag the lens. I'm going to choose that I'm going to separate by 0.5 meter. So this is my lens. Maybe I call it lens 1. I'm going to go at 0.5 meter away. So let's say 0.9 meter. And I'm going to use a cylindrical symmetric lens. And so I'm going to use a similar focal length for both plane. And this is going to be the same as the distance I choose. So I'm going to put it at 0.5 meter in both planes. And then I close. And then I'm going to put another watch point. And this watch point, I'm going to put it at 0.5 meter. So this is going to be 1.5 meter from the lens. And so if I run this, what I should see is just an image of the source, because now I just have one lens, and on each side I have 0.5 meter, and the focal length is 0.5 meter. So I should this source here that I made, it should be imaged in this watch point plane. So let's see if it works. So now we have 3 watch points, well, plus the initial intensity distribution. So and this guy should be very similar on the last one. Apparently I did something wrong because I use 1.5 meter, and it should be 1.4 because I add 0.5 meters. So let's see. So let me just. Okay, it's not really an image for now, except. Oh, sorry, I got. Yeah, the scale are different. So, okay, I don't. It's not really an image right now, but I just want to continue to make to show the frequency filtering. So let me. It should not affect that. So let me now put an obstacle. And I'm going to put this obstacle at 1.4 01 meter. I think my rounding is a bit wrong, so that's why I'm kind of not having a perfect image. And I'm going to use an aperture. Let's say an obstacle with let's say 2 millimeters. So I'm sure I suppress all the low frequency. So here you see, if you look at this guy, what I'm trying to do basically with this obstacle, I'm trying to make sure I mask the central region and only the high frequency, which is this outer ring that you can barely see, but you can see the projection is transmitted. And this will ensure my final source will only show the edges, its edges. So I have my obstacle, and then I'm going to do the symmetric. So put one more lens, and I'm going to put this lens at 1.9 meter. I'm going to have it at 0.5 meter focal length in both plane. And then finally the watch point, which will give us, hopefully, the image, so 2.4 meter. So now let me run this, and what we should see is an image of this, but with some of the frequency suppressed. So it should be something close to a ring. So let's see if it works. I think I did something wrong with the final watch point. The final watch point should have been, oh no, that's okay. Yeah, that's okay. So you see, now you can see we have an image of this guy, but if I zoom, so here I had, you know, the beam looking like this. Let's see, can I move this guy here? I think I might have to do something like this. Okay, so we can compare. And I don't know why I lost this one. And this one is the final one. You see, it's kind of course, again, I'm limited by the resolution, but what I did by putting this obstacle in the middle, I suppress the low frequency. So now you kind of see more the edge than the center of the beam. Okay, and last example I wanted to discuss, which is already all set up, so it will be very fast, was undulator radiation. So if I show this guy, what you can do in SRW, you can set up an undulator. So what I did here, I set up an electron beam which has the parameter of the iota ring, so 100 MeV should be 100 MeV electron beam. Because I'm doing single electron calculation, I don't care about all these things. And I set up an idealized undulator, which is similar to iota, so period of 77 millimeter. Sorry, a period of 11 millimeter, no, 11 centimeter, and length of 77 centimeters. And so what Georg already showed all this, but as you know, as it was discussed, what happened is that you have this umbrella, except that my umbrella is tilted by 90 degrees. And so you expect to see the spectral angular fluence that looks like this. And what is this first umbrella, tilted umbrella, labeled as 1 is the fundamental frequency, which or wavelength mode, let's say, which in our case is about 2.2 micron in wavelength. And then you have the second harmonic, which as was hinted, has no field on axis, but has side lobes. And then you have the third harmonic, which has intensity on axis, and then the fourth harmonic, and so on and so forth. This was actually calculated with RCW. So what I would like to do now is to simulate this this undulator and show you some of this property. So let me, well, actually it's kind of already run, but let me go to, actually I will stay only in the source, I don't need the beamline here. So this, let's say, sorry, I need to look at my, so the, I want to change something to refresh the simulation. So let me do something that was mentioned earlier, was imagine I just, oh, I cannot do that. The problem is that if I change something, I'm going to have to retune many parameters. So let me not do that. So what is done here, I set up my undulator, it runs, and then I produce the spectral distribution on axis. So for instance, this is, let me maybe do even more so I can see up to 4 and do 2000 points. So you see it running at least. So this is the spectrum on axis, and this means that I would have a line on the axis at the observation point theta equals 0, and so you would see only the first harmonic and the third harmonic and maybe a higher odd harmonic, and this is what happened here, you see. So it's in energy, and the energy is related to wavelengths using this formula. So anyway, this is 2.25 micron. Wavelengths, the first one at 0.55 eV. Then you have the third harmonic, the fifth harmonic, and the seventh harmonic. Now, what I can do also is I can compute the spectral flux and what it is, and let's say it's arbitrary unit because the units are always renormalized with the current, and I don't want to go to it. It's a bit complicated to explain right now. So what is shown here is the flux that is integrated. So let me just put a point and go to 4. Shown here is the spectrum that I would compute if I would take the full radiation over an aperture, meaning an angular opening gamma theta, which go from, for instance, -1 to 1, and do the integral, do the projection, and then do a plot this spectrum, which is shown as a white line, here. And so in this case, you see what happened is you start to have this second harmonic appearing, because as you do the projection, you have this signal into the angular opening, this information. And then the last thing, well, I should have said this first, actually. These radiation are computed for first principle, and so the first thing SRW does, it tracks one electron through the trajectory. Here it's an idealized undulator, and this is what is shown on the bottom right plot. Finally, you can also plot the distribution of the radiation in XY. So here I choose the 0.55, which is the peak. But as you go off axis, what will happen is that if I decrease the energy, I'm going to sample the side lobe of the umbrella here on 1. And so let's try to see that and see if I go to 0.6, for instance, I should have a ring now. Hopefully, because I should sample the side lobe of this guy. So you see, well, it's not yet a ring, so I was too close still. Let me try one more point before. So maybe probably I go further away. And of course, so I forgot to say the ringing you see around is because of the. So you see now you have more like the donut pattern at the center. And all these things around, some are due to artifact because I'm using a small grid and of the boundary, and some are due to the fact that, you know, if you go far enough, some of this umbrella are folded too, but I don't think you can see that here. Okay, so that's all I wanted to show for now. As I said, it's a very high-level intro, but hopefully it can be useful. And just to point out that this Sirepo is an interface to several code. All the list is here right now. And some like Opalty, actually, we are using in our group. This is a spatial calculation similar to Astra or GPT, elegant, that I guess many people know. And Warp VND, which has been used to do cathode emission simulation. Okay, that's all for now. Any question? Did anybody try actually to run this at the same time? Or?
Philippe, can you do coherent processes like FEL?
Yeah, actually, yes. Yeah, it's beyond that, but yeah, there is a way to have a multi-particle summation, so you can do a coherent radiation. And it has been done so you cannot do the FEL process, but it has been done coupled to Genesis to study propagation of FEL pulse in systems. So I should say, when I say it has been done, probably not the Sirepo, but the SRW, which is under.
What does it add to Genesis? I thought Genesis has the field in it already. Why do you need SRW?
Or if you want to simulate the beam through a beamline, look at this. I think at DESY people were looking at this Young interference, to show the transverse coherence of the radiation. So all these were simulated with some version of SRW.
So you propagate the field from Genesis.
Yeah. And so it does, but yeah, you cannot simulate from first and principle the SASI FEL, for instance. Yeah. But you can input some kind of bunching factor and look at the radiation, the coherent effect. Yeah.
So can you actually with this put like a crystal and see diffraction out of it?
Yes, there are some model of crystals actually. Yeah. Yeah, you can see here. I mean, I don't know, but you can have the material, the orientation, the geometry. So there is ways of doing this.
Oh, nice.
Yeah. So yeah, I think there is a few there are a few papers on people doing pretty fancy things in terms of propagating X-ray. So this I forgot it's called elliptical grazing incident mirrors and all these things up to the sample. Yeah.